Imagine a computer so powerful that it could solve problems today's fastest supercomputers would struggle with. A computer capable of designing new medicines, discovering advanced materials, optimizing global logistics, and one day solving mathematical problems that have protected digital communications for decades. That is the promise of quantum computing. But despite the headlines, quantum computers are not simply faster versions of the computers we use every day. They are built on an entirely different way of processing information. To understand why, we first need to understand one simple idea: the difference between a bit and a qubit. Every computer you've ever used, from your smartphone to the world's largest supercomputer, is built using bits. A bit is simple. It can only exist in one of two states: 0 or 1. Everything you see on your screen, every website you visit, every photo, every email, every financial transaction, and every video is ultimately reduced to billions of these tiny binary decisions. Quantum computers use something very different. Instead of bits, they use qubits. Unlike a classical bit, a qubit isn't limited to simply being 0 or 1 while it is being manipulated. Instead, it exists as a quantum state that can be carefully controlled before it is measured. Only when we finally measure that qubit does it produce an ordinary classical result, a 0 or a 1. That might sound like a small difference, but it completely changes how certain problems can be solved. Quantum algorithms don't work by trying every possible answer one after another, and they don't magically know the correct answer either. Instead, they manipulate probability using uniquely quantum effects. One of those effects is called superposition, another is called interference. Think of throwing two stones into a calm pond. Where the waves meet, some waves grow larger while others cancel each other out. Quantum algorithms work in a surprisingly similar way. They are carefully designed so that incorrect answers interfere with one another and become less likely, while the correct answers reinforce each other and become more likely. Then comes another remarkable phenomenon: entanglement. When qubits become entangled, they stop behaving as completely independent pieces of information. Instead, they become linked together as part of a larger quantum system. This allows quantum computers to represent and manipulate relationships that become extraordinarily difficult for classical computers to simulate. It is this combination of superposition, interference, and entanglement that gives quantum computers their unique potential. But there is one enormous problem. Qubits are incredibly fragile. Even tiny amounts of heat, microscopic vibrations, electromagnetic interference, cosmic radiation, or imperfections inside the hardware itself can destroy the quantum state before the calculation is finished. This process is called decoherence, and it is one of the biggest challenges in all of modern engineering. Imagine trying to balance thousands of spinning coins on a vibrating table for several minutes inside a hurricane. That gives you some idea of the challenge researchers face. This is why simply counting qubits tells us very little. The real challenge isn't building more qubits, it's keeping them stable long enough to perform useful calculations. That is where quantum error correction comes in. Researchers combine many unstable physical qubits together to create a single, much more reliable logical qubit. A logical qubit isn't new hardware, it's an engineering achievement. It represents quantum information that can survive long enough to perform meaningful work. This is why logical qubits, not physical qubits, have become one of the most important measures of real quantum progress. Once enough reliable logical qubits exist, increasingly difficult computational milestones become possible. One useful way to think about that progress is as a capability ladder. The first major milestone is around 100 logical qubits, an important scientific achievement, but still far from practical cryptanalysis. The next milestones involve small demonstrations of Shor's algorithm, the quantum algorithm famous for factoring numbers, and solving certain mathematical problems much faster than classical computers. Initially, these demonstrations work only on tiny educational examples. As logical qubits become more reliable, larger cryptographic systems become possible. Researchers may eventually demonstrate attacks against 64-bit keys, then 128-bit systems, followed by 512-bit RSA, then 1024-bit RSA, eventually reaching RSA-2048, one of today's most widely recognized public key security standards. Beyond that comes elliptic curve cryptography, used extensively throughout the modern internet. And eventually, if quantum computers continue advancing over many years, systems based on exposed public keys would become increasingly vulnerable unless they had already transitioned to quantum-resistant cryptography. The final milestone would be large-scale practical cryptanalysis, a point where fault-tolerant quantum computers become capable of performing reliable attacks against major public key cryptographic systems. That is still an enormous engineering challenge, and one that requires far more than impressive headlines or large physical qubit counts. It requires stable logical qubits, powerful error correction, exceptionally low error rates, deep quantum circuits, and years of continued engineering progress. Quantum computing is one of the most exciting technologies of the 21st century, but it is also one of the most difficult engineering challenges humanity has ever attempted. The future won't be defined by who builds the biggest quantum computer. It will be defined by who builds the most reliable one. Because in quantum computing, stability is everything.